So, yeah, so let's start with the challenge statement webinar today. And to brief what's going to have in the webinar is I'll just touch on the quick agenda of what we're going to talk about. So it will be like a brief introduction of Adcorpus, and we'll be giving you a quick overview of what's challenge statement is about and what's the problem and why it matters. And following with that, we'll be just talking about the assessment overview, like how we're gonna assess this year, whether it's gonna be like a report or just a presentation and stuff like that, and what how much mark weightage and everything. Following with that, we'll be talking about the key factors that you guys have to consider when addressing the challenge statement. And then we'll be talking about the methods to evaluate and demonstrate the power efficiency. Then we'll be opening the platform and you guys will be asking the Q&A questions and we'll close the webinar. So just before we dive in, I would like to take a moment to introduce today's speaker and to extend a warm thank you to Adcorpus, our platinum sponsor for this event. And Adcorpus is led by Nicholas Barabino, who joins us today as both a sponsor and a key contributor to this Heart Hackathon. Nicholas is a founder and principal consultant of Adcorpus, and his background is about as well-rounded as it gets in medical device development. So he holds a PhD in microelectronics and brings over 15 years of hands-on experience taking complex medical devices from early concept all the way through the clinical stage. His specialization sits at the interaction of two fascinating and fast-moving fields, active implantable medical devices and wearable technologies, with particular focus on cardiovascular and neurotechnology applications. What sets Nicholas apart is not just the depth of his technical expertise, but his ability to operate strategically across the full development lifecycle. He's led multidisciplinary R&D teams across both startups and established industry players, which means he understands the real world problem that actually needs solving. And that's exactly why we are thrilled to have him here today. And Nicholas will be presenting challenge statement for Heart Hackathon 2026. So please join me in welcoming Nicholas. Thanks for today's presentation, Nicholas. And we just, yeah, over to you. You can talk about it.
Thank you, Madhu. Thank you very much for this very kind introduction. And it's a pleasure for me to present today, to participate to the hackathon, to sponsor it. And yeah, I really look forward to now describe the challenge and then staying involved throughout all the process. So to start, what's Adcorpus? So as Madhu was saying, we're a consultancy company based in Barcelona, Spain. And we specialize in active implants and also other complex devices like wearables that stimulate the body, sense, or have some kind of invasiveness. So our key values are expertise and flexibility. We are a small team, but we accumulate a lot of experience in bringing devices from concept to market in areas such as neurostimulation and cardiovascular devices. So here's an overview of the active implantable medical device space. As you may already know, there are devices that can help with neurological disorders, stimulating the brain, also other parts of the nervous system, like spinal cord stimulators for back pain. There are also devices that stimulate for treating conditions such as overactive bladder in the tibia. There are also cochlear implants for restoring audition. There are also, of course, pacemakers, which is the first active implant, which is its first implantations were in the early 60s. So you can see that there's already quite some experience with that kind of device. Defibrillators, of course, heart pumps and artificial hearts, and also drug delivery devices like insulin pumps and also the drug delivery devices for pain relief. So this is are just some examples. There are many others. It's a very exciting field, as you can imagine, very challenging. We are working with the cutting edge electronics, mechanics, but also interfacing constantly with the body. So there are a lot of considerations, a lot of requirements from regulators, of course. It's a very regulated environment. It's very difficult to get to the market for, of course, for good reason, right? Because it needs to be demonstrated that the device is safe for the user, for the patient and other users, and also that it's that really brings benefit to the patient, right? And as you can imagine, it takes very long time to go from concept to market. It's estimated that it takes no less than 5-7 years for the less complex, less invasive devices, implantable devices. And in some cases, it can take 10, 20, 30 years. So it's probably the most complex kind of medical device, or one of the most complex kind of medical device that exists. And so coming back to Adcorpus, what we do is we provide engineering services for developing these kind of devices. And how we do it? So as I said, our key values are expertise. So we have a team with a lot of expertise in the key areas involved in developing this kind of device throughout all the development life cycle, and also flexibility. That means that we adapt to the different stages and also to the specific needs of each client. So in some cases, for instance, a customer comes to us at a very early stage, what something that we really prefer, right, to start contributing from the beginning. And there it's not really about development or design. It's mostly about strategy, building together with the client a roadmap, from moving from that early concept that they have or they want to develop towards something that can actually be implanted and can be approved for its use and benefit the patients. And then we can also work in the initial stages, prototyping, doing all the systems engineering work, which is, of course, as in any other area where the devices are complex, is key to have a very systems engineering groundwork, establishing clear requirements, architecture definition, then also reviewing the standards and other regulations, and making sure that from the requirements, the device is compliant with the expectations of the regulators. Then doing the detailed design, of course, according to the standards and following the design controls that are required, doing verification testing, and then transferring to manufacture. And here's a explode view of an example of some of the devices we work. So as you can see, so this is an implantable device, right? So it has titanium enclosure. So as you may know, titanium, it's a very well-known biocompatible. It's very well known for its biocompatibility in the long term. So usually, most of the devices that are implanted for the long term have titanium enclosures. So, and on the inside, there are the components that you might expect, PCBs with electronics. There are also batteries in this case. Not all implantable devices have batteries, but this one has a battery. And then there are other components for interfacing with the exterior of the device, like connectors, implantable grade connectors. These devices can also have Bluetooth wireless communication. So this one in particular, we designed as a Bluetooth antenna, not inside the titanium, of course, but in an external compartment filled with epoxy. That it's also where the connectors are housed. Yeah, it's that's like the basic architecture of classical active implant. And here is just the team. So myself, I reintroduced myself. We also have Erika Fernandez, head of operations, who's an industrial designer with a lot of experience in active implants. And also Enrique Calderon, our system lead, has a lot of experience in active implants and drug device combination products. And we are, as I said, based in Barcelona, a team with electronics, mechanics, biomedical, and software engineers. And that's it for Adcorpus.
Thanks, Nicholas. And this we can continue with the challenge statement of this year, and we can proceed with the following. Yeah.
Great. Okay, so yeah, I read the statement and then we can comment on that. So yeah, as you already know, the challenge is addressing power efficiency. So how can your total artificial heart be more power efficient to reduce the size of wearable components and improve patient quality of life? Teams may consider spending time enhancing the power efficiency of their device and demonstrating efficiency values in their report. Future work to further enhance efficiency should also be detailed. For new teams who are not yet able to focus on power efficiency, they should focus on what methods will be applied in the future to improve this.
Yeah. So how this will be assessed is like this time it's just going to be assessed through the final report. Last year we did have a split of marking both in final presentation as well as in the report, but this time we are just focusing on the report marking. And so as we have circulated before, the final presentation has pattern has been changed. It's more like a business pitch, so you can just focus on that. And this will be purely through marking the challenge statement, and we'll be giving the award based on that. So how we gonna mark is like maximum it's gonna be 800 words, and you can just put up to 5 figures or tables, and this will be marked for 10 marks. So that will be split into four 2.5 marks for each topics, which is problem statement and root cause analysis, suitability of design, and novelty of the design, and how we are planning to roll off this strategy and your future work. So this is the basic framework that we have for this year. And Nicholas will be talking about this.
Okay, so the aspects to consider for the challenge. I would say that the first thing that should be considered is that this is, of course, a complex system with multiple subsystems for the actuation, subsystems for driving the actuator, then other electronics, and losses could be everywhere and are everywhere, right? So I think the first thing is to have a clear, it's important to have a clear breakdown of the system and to analyze one by one the subsystems to identify where the main losses are, then to start preparing a strategy for reducing those losses. Another important consideration is to check the industry standards. I think that here the idea is actually to check what to have a benchmark. So what other devices that could be total artificial heart or ventricular assist device or any other device that has a similar actuation mechanism, and so understand what the efficiency that has been achieved, right, by other designs, and yeah, to use it, as I said, as a benchmark for this design, and to understand where the main roadblocks could be, right? Why it hasn't been possible to be more efficient. For instance, something that is quite well known is that there's a trade-off when you pump blood between the efficiency and how I mean, yeah, how compatible it's the pumping with the blood, right? So if you want to be very efficient, it's possible to have good efficiency figures, but it might come with a cost in the biocompatibility. It might lead to hemolysis or other damage to the blood. Then, of course, to consider alternative drive mechanisms. So as you know, some people use rotary motors, other linear actuators. And of course, this depends how you actually interface with the blood. So I think it's a good idea to be open-minded about the methods that are used for driving the for actually pumping, and that considering alternative methods could bring in efficiency gains. Then power transfer. So as you know, it's very artificial heart is very power hungry, and it's very difficult with the technology that's available today to have something that uses wireless power transfer. But yeah, it's of course one of the main drivers for being efficient, and is something that could be considered from the beginning and see how yeah, it could be factoring eventually as the design moves forward. And then another very important consideration is to check efficiency across the operating range and not just the best efficiency point. I think that it's definitely complex to know how efficient it could be across all the operating range, and considering like a normal use profile, right? So for instance, fluctuations during the day. So the patient might need more or less support throughout the day. So it's difficult. There's some add complexity, but it's key, because if you only optimize one operating point, let's say that your design is only very efficient when flow is 4.5 liters, it might not be relevant if flow is moving around, and it's maybe sometimes 4, other times 7 liters, 3 liters. So it's definitely very important from the beginning to have this holistic view of the efficiency. And then about methods to evaluate, demonstrate power efficiency, computational and physical. So as I mentioned before, it's very important to provide a detailed breakdown of the device, right? Subsystems like hydraulics, electronics, motor, power transfer. Do not start analyzing the efficiency before breaking down the system and analyzing subsystem by subsystem. Here you can use computational or physical methods, for example, multi-physics simulation software. Then, of course, once you have a model for the efficiency of each subsystem, to create a model for the complete system efficiency. And then use it to evaluate the different design trade-offs, right? So how changing the design of a specific subsystem or component changes the overall efficiency, considering that it might also impact how other subsystems work, right? It might change the operating points of other subsystems, and that might also change their efficiency. So once you have a model, of course, you can prepare a plan for improving the efficiency, planning improvements on at each subsystem level, and yeah, keeping the overall efficiency model as the main tool to evaluate the efficiency gain. You're mute.
Thank you, Nicholas, for explaining us how to do and what to do and what can they expect from this challenge statement and stuff. And anyone from the call have any other questions on the challenge statement?
Maybe, Madhu, before the questions, I would
Hmm.
think that something important to highlight is
Sure.
maybe we didn't explain it at the beginning
Hmm.
is why we need to be to have efficient um, hearts, right? Total visual hearts, and
Yeah.
so it's definitely important because of the quality of life. And that's because if you have very high power consumption and your device has external batteries, as is the case with most mechanical circulatory support devices, those batteries will need to either be very big and difficult to carry for the patients, or might need to be recharged very frequently throughout the day. So
Hmm.
there's a big impact in the quality of life, and so it's not just the fact of having a driveline, which is already a problem for patients, but also the management of the external devices, and the impact of the external devices is directly related to the efficiency. And then, of course, the ideal solution would be to have no driveline, to have only implantable, full implantable system, which, as of course, is that possibility is linked to the efficiency, right? If
Yeah.
the heart reaches power consumption that enables using transcutaneous energy transfer and storing the energy in an implantable battery.
Hmm.
Yeah, it could be possible to design a system with those characteristics.
Yeah, that's true. And Nicholas, just before going to the question, like how small do you think the battery has to be designed for these type of devices?
How small the battery needs to be? Okay, good question. So as I said before, it's important to have a benchmark. If we look at left ventricular assist device, so as you know,
Hmm.
it's the most yeah, widely available mechanical circulatory support device. They have couple of batteries of about 80 watt hour, and
Okay.
in terms of size is maybe something like yeah, 10 by 20 by 3 centimeters, or a bit bigger than that, two
Hmm.
blocks like that. And so that's probably enough for about yeah, 12 hours of operation.
Okay.
Um, so yeah, I encourage all participants to take a deeper look at this. So look at the brochures of these devices, go to the websites of the manufacturers, download the data sheets, and better understand yeah, how the wearables, the batteries in particular look like.
Mm. Yeah. Thanks, Nicholas. And any questions from anyone?
Yeah. So I had a question about the challenge statement itself because it was like stated that the reason why we want the power efficiency is to reduce the size of it. I was also wondering if you would consider like reducing the heat generation by increasing the power efficiency with the challenge statement as well.
So I don't understand the question. So if Of course, reducing power consumption will lead to reducing heat dissipation. Your question is if that's also part of the goals to demonstrate that you release less heat.
Yeah. So like I guess the thing is would uh by us like writing down like the amount of heat generation, would that also sort of correlate with I guess support our power efficiency of like our device, I guess. Because like yeah.
Yeah, I mean, if you change the design in a way that it releases less energy as heat, that will have a direct impact in the power consumption, right? So you should be able to see that in the power consumption, and so you'll be yeah, moving in the direction of the challenge. I think we lost him.
I think there might be some network issue. Yeah. So Nicola, as Nicholas was saying, like size and the heat dissipate efficiency is actually correlated. Like the when you reduce trying to reduce the heat, the size is, I mean, when you try to reduce the size, the heat dissipation is also has to be considered in development, right? Yeah. Any other question from anyone?
Hello.
Yeah, we can hear
Hello,
you.
Nicholas. So my question is also relating to the challenge statement. So it's regarding well, similar to that guy, as well as relating the power efficiency to reducing the size of the wearable components. From my understanding, there are some instances where adding additional components, such as like electronic switching, for example, can help to improve the efficiency instead, rather than actually like removing components to improve the efficiency. So would that be contradicting the challenge statement if our design were to add additional components? Will it technically increase the size of the wearable components to improve the efficiency?
Yeah, I see your point. No, I don't think. I mean, if you're adding some circuitry to reduce power consumption, I think it's very unlikely that what you gain in terms of yeah, reducing battery size, you lose it as increasing circuit size because it's uh, it's normally yeah, much smaller the size of the circuit that you need to add. So yeah, yeah, I don't think that it's relevant, but it's interesting to think about it, of course.
Also, the wearable components are more on the larger components, like the battery, basically. Okay.
Yeah, yeah, yeah. So that's what I mean. That so the batteries, if you get to reduce the battery size, probably you will not offset that by the circuit that you need to add, right? By if you need to make your controller enclosure bigger, probably will be still compensate for the gain.
Okay. Thank you very much. And also like a follow-up question. So when you are assessing the efficiency of our system, um, so we should be presenting like the efficiency of like multiple, how do I say, like the steps, like the power transfer efficiency as well as the mechanical efficiency and well, the overall efficiencies.
Yeah, that's what I described. That yeah, it's important to have a good breakdown. So breakdown of the system, right? Separate in subsystems and then analyze the efficiency subsystem by subsystem.
Okay. Thank you very much.
So I was wondering what physics simulation softwares could we use, and are these like physics simulations more for like electrical base or is it mechanical base? Just as
So I think that in this case it's mechanical based, right? So for the electronics, yeah, you don't need to choose for this kind of electronics multi-physics simulations, right? So any good electrical circuit simulation tool would do the job for calculating the efficiency.
is there any like suggested electrical simulation if you could?
Yeah, so LT Spice is very popular and very powerful. So I recommend that one.
More question, guys? Yeah.
So I don't know if this is like related, but like I was wondering about how can we because we're gonna have electrical components within the total artificial heart. So I guess my thing is how can we prevent components from getting short circuited by like the blood that flows through it, like the heart?
Mhm. Good question. Yeah, of course, you need an hermetic compartment, right? So in the slide I had where I showed the explode view of a device, you can see the PCB. It's housed inside a titanium enclosure. And so it's designed to be hermetic, so completely sealed, right? So there's no liquid that can penetrate that enclosure. And so, yeah, that's how you make sure that the electronics operate. There are other materials, other way of encapsulating, but yeah, this is what's most widely used.
Um, Sorry, another question. So if a device use like a has a magnetic component to it, is there like a concern with, I guess, outside magnetic fields? Like for example, if someone used a MRI machine, would could that be
Yeah, of
considered?
course. Yeah, it's contraindicated, right? So MRI is not compatible with implants that have magnetic components. It's also it prevents components that have maybe not they're not magnets but have certain yeah magnetic properties. So ideally, an implant for being able to undergo an MRI scan has to be metal free or almost free of metals. So there are some examples, devices that have been designed with different materials, right? Now titanium, and also yeah, as less copper as possible, and yeah, they are almost transparent um, under an MRI scan. But devices like the one I'm showing here and a total artificial heart very probably are not compatible with an MRI scan.
I do.
Okay. Yeah.
I was wondering, could this be also extended for like possibly like the power pack itself? And like, because at the end of the day, for most of us, you would have a way to like carry the device like around throughout the day. Um, and so would you also consider like extending the challenge statement to the usability factor as well by um, having more having better power efficiency, you can also like have better usability factor as well for people who So instead of needing to change the battery constantly, you have a better power efficiency, so you have long-term use of battery life as well. Is that also an extent to this challenge statement as well?
Yeah, no, interesting point. As I was commenting earlier, its usability is of course one of the most important considerations for designing one of these systems. I would say that it's actually what you just described, right? The trade-off between having small batteries and more recharge cycles, and or having bigger batteries and less recharge cycles. That's maybe quite independent from this challenge, because what I would assume is that whatever configuration you target, it doesn't involve any very frequent recharging, right? So I think, and as I also said, it's very important to look at the industry, what's actually being used. And so I think probably patients are expected to recharge their batteries once, twice per day, right? So I would expect that you consider something like that, similar to that. So by keeping that constant, let's say, if you reduce power consumption of the system, you will directly impact the size of the batteries and the overall user experience.
Thank you for that.
So for the challenge statement, what is sort of the application of it? Is it for, are we writing a report or something? And if so, like when would that be due? Or is it sort of a thing to consider within our team as we write up the final reports for the Heart Hackathon?
Yeah, so this will be submitted during the final report. So it will be the part of the final report. Like you will be having a extra additional 10 points for this. So these are the distribution of marks and the word count and this figure as well. So it's just a format is just like a template, but you can just improvise or you can modify based on your idea.
Are there other challenge statements, or is this like the main thing that they're looking
This is the
at?
only challenge statement for this year. Like similar to the how we had like one extra challenge statement last year, apart from the hackathon event, like about TAH. So this is the similar to one. So this is the only statement we have. Challenge statement. Any more questions, guys?
Is it possible to reach out for if we have any other questions? Maybe to
Yes, of course.
Nicholas.
Yes, feel free to reach out. Yeah. I think there's my contact information here, or otherwise, just send an email to the contact email for our company Adcorpus, right? Or you can also contact me through LinkedIn. So feel free to reach out if you have questions. And Madhu, before we finish, can I do an announcement? Because we're organizing an active implants event here in Europe that might be interesting for the students located in Europe or nearby.
Sure, you can do it. And also we can just advertise to our shows through our socials as well, like in
Okay,
LinkedIn and stuff.
great. So maybe I can now share my screen, show the website, and then I
Okay,
can send information so you advertise it.
sure. I'll stop sharing.
So here it is, active implantable medical device workshop. It's 4 or 5 June, so in less than 1 month. So it's quite soon. It's so in the Netherlands, and this is the third time we do it. It's last time was in Barcelona, here where we are located. This time we go to Delft, and we do it in partnership with TU Delft. It's a university that has a very strong biomedical engineering team that has a lot of work in active implants. So we are co-organizing with Professor Outer Serding. The goal of the event is to connect the industry and research and across all the active implants applications. So we have neurotech, bioelectronic medicine, cardiovascular devices, implantable monitors, glucose sensors, also topics related to electronics, fabrication. We also have visual prosthesis, cochlear implants, regulatory. You can take a look at the speakers here. You will see that the scope is very broad and very interesting. And so, well, we have maybe some of you know Libera Fresiello, who's an academician in this field, mechanical circulatory support. We have somebody from CoreWave presenting. So mechanical circulatory support devices are well represented. And registrations are still open. There are discounts for students. Unfortunately, it's too late to present a poster. Registration deadline is in 15 days. So if you are interested, I encourage you to take a look at the program and the registration. I think it's really can be really formative for students that are now interested in this field. You can connect with researchers, but also with the industry. And if you're interested in continuing your career in this field, might be a great opportunity for starting to explore that.
That looks like a great opportunity to network and just get along and learn more as well.
Yes.
All right. So we can close the session. If at all you guys have any more questions, you can reach out on Nicholas directly, or you can just let us know, or we can just talk to you about the answers and stuff like that, like regarding the assessment and everything. And thanks, Nicholas, for the great webinar, and good luck with the event next month and like during June. Yeah.
Thank you, Madhu. Thank you,
you.
everybody.
Thanks,
It was a
everyone.
pleasure.
Yeah.